Abstract Factory solves a compatibility problem. A client needs several related objects, and each object can be valid on its own, but the set only works when every member comes from the same family. Its defining characteristic is one creation boundary for that family. The client chooses a factory once, then receives products designed to work together. In Part 1, we will build a Rover protocol twice, first as a clear direct composition, then with Abstract Factory after the risk is visible. The example, code, diagrams, and wording are original. There is no ASP.NET Core, dependency injection container, or third-party package. The client starts the collaboration, but depends only on abstractions. The Abstract Factory declares one creation method for each kind of product in the family. A concrete factory implements those methods and chooses compatible concrete products. Product A, Product B, and Product C are roles, not inheritance levels. They represent different responsibilities that must agree. One family might provide a command encoder, telemetry decoder, and safety policy for a rover. Another family can provide the same three roles for an orbiter. The client still speaks through the product contracts. The concrete factory is the only object that knows which implementations belong in the selected set. That is the central distinction from factory method. We are protecting a family of related products rather than one product created inside one creator workflow. Abstract Factory is useful when products are consumed as a set, several families are meaningful, and mixing families can produce bad behavior even though every object satisfies its interface. Typical use cases include theme components, database driver parts, device protocols, and controlled test environments. Keep the design direct when there is one product, when products vary independently, or when the caller already owns the exact objects it needs. Constructor injection or a small creation function may be enough. The cost is real. We add contracts and concrete factories, and adding a new product role changes every family. The pattern earns that cost only when compatibility is a domain rule rather than a preference for tidy construction. Our session sends a mission command, reads telemetry, and checks whether the command is safe. Those jobs belong to three separate products: an encoder, a decoder, and a safety policy. The family name is a fourth value the result reports. A direct composition can pass all four choices into the session. That is readable, testable, and completely reasonable while we have one Rover protocol. The pressure appears when another protocol arrives. A Rover encoder, an orbiter decoder, and a Rover safety policy can all satisfy their contracts while disagreeing about codes, units, or limits. The bug lives in the combination. We will keep the direct design first, prove it, and then move ownership of that combination. Open the empty contracts file and type the shared language before any concrete family exists. Mission operation is a small enum with drive as the only operation Part 1 needs. As mission command is typed, the record pairs that operation with a numeric value. Telemetry frame is a read-only record struct because it is a compact value that we pass by value. Safety decision reports whether the command is allowed and explains the result. Mission result gathers the family name and the three observable outputs. Now define the product contracts. As iCommand encoder is typed, its single method turns a typed command into the wire representation. iTelemetry decoder translates one frame. iSafety policy evaluates one command. Each interface has one responsibility and none mentions a rover. Before the final contract moves below the fold, let the editor scroll so the complete method stays visible. Switch to the empty Rover file and build each concrete product in the order the session will use it. As Rover command encoder is typed, the class name identifies both the family and the role. Its switch expression accepts a positive drive command and produces a Rover wire value, such as RV drive 012. The fallback remains explicit for unsupported input. Rover telemetry decoder reads code 7 as a battery percentage. Any other code becomes unknown telemetry instead of pretending it understands the frame. Scroll before the safety class reaches the bottom of the editor. As Rover safety policy is typed, the property pattern checks the same drive operation and limits its value to 25 units. It returns a safety decision rather than throwing for an expected rejection. These three classes agree on Rover command semantics, telemetry codes, and movement limits. They form one family, even though they implement different product contracts. Open mission session and type the direct version. As mission session is typed, its primary constructor receives the family name and all three product interfaces independently. That is ordinary constructor injection. Run first asks the safety policy to evaluate the command. As encoded command is typed, the conditional expression makes the boundary visible. An allowed command reaches the encoder while a rejected command becomes blocked. The result keeps the supplied family name, decoded telemetry, and safety reason together for the terminal. The workflow depends only on product contracts, so it is already easy to test. Nothing is wrong with this class. The question we will ask after the run is who should be responsible for assembling a compatible set. Move to the empty program file and make every composition choice explicit. As session is typed, program supplies the Rover name, encoder, decoder, and safety policy one by one. The success path sends a 12-unit drive command with battery telemetry at 86%. As blocked is typed, the boundary path changes only the distance to 40, which is beyond the Rover limit. Both calls use the same session, so the comparison isolates the safety decision. The output includes the family, encoded command, decoded telemetry, and reason. This client is longer than a factory-based client will be, but length alone is not the problem. Its real responsibility is choosing 4 values that must stay compatible. The direct version compiles and runs. The success path reports the Rover family, an encoded 12-unit drive command, battery at 86%, and an accepted safety decision. The boundary path keeps the same family and telemetry, but blocks the 40-unit command. Both results are correct. Pause on the 2 lines because this is our behavioral baseline. Abstract Factory must preserve it. We are changing ownership of the product set, not repairing broken domain logic. Now the pressure is concrete. Program owns 4 independent decisions, the family name and 1 implementation for each product contract. With 1 family, that explicit code may be the clearest design. Part 2, however, will add an orbiter protocol with different wire values, telemetry codes, and safety limits. Every caller would then need to remember which 4 choices belong together. Abstract Factory moves that compatibility rule into a family object. Program will choose Rover Protocol Factory once. Mission Session will ask that factory for the encoder, decoder, and safety policy. The decisions do not disappear. Their owner changes from every composition root to the concrete family that understands them. Return to mission contracts, move to the end, and add the family-level contract. As Mission Protocol Factory is typed, its name says that the object creates one mission protocol family. Family name travels with that choice instead of arriving as unrelated text. The next 3 methods correspond exactly to the product interfaces we already built. Create a command encoder, create a telemetry decoder, and create a safety policy. Their return types remain abstract. The contract guarantees the shape of a family, while each concrete factory decides which implementations it returns. This interface is the abstract factory participant. It does not run the mission workflow, and it does not replace the product interfaces. Its job is narrower. Keep the creation decisions for one compatible set behind one boundary. Switch back to the Rover family and continue below the 3 products. As Rover Protocol Factory is typed, this class becomes the concrete factory. Family name reports Rover. Each creation method returns the concrete Rover product for its role. The methods are deliberately plain. The value comes from owning the set, not from hiding complicated construction. These products are stateless and inexpensive, so new instances keep the example honest. A production factory could receive family-specific dependencies through a primary constructor when that is part of the design. Here, the 3 explicit new expressions make the compatibility decision easy to inspect. Return to mission session and rebuild its short implementation around the new boundary. Its primary constructor now receives one Mission Protocol Factory instead of 4 separate values. As protocols is typed, the private property validates and stores that required dependency. Run asks the factory for an encoder, decoder, and safety policy before following the same workflow as the baseline. The safety decision still controls whether encoding occurs. Telemetry is still decoded, and the same result is returned. The family name now comes from the same object that created the products. That small change is the guarantee we wanted. Mission session cannot be constructed with a Rover name and an unrelated decoder through its public API. The workflow still depends on abstractions, but compatibility now has one owner. Move to program and retype the client with one deliberate change. As Rover Protocol Factory is typed, the composition root chooses the Rover family once and passes that factory to mission session. The telemetry, success command, boundary command, and output lines remain the same. This shorter constructor call is useful, but the stronger result is responsibility. Program no longer knows the concrete encoder, decoder, safety policy, or family name string. It selects a family. The concrete factory owns the members of that family. Run the program again. The accepted path still produces the Rover command, battery telemetry, and accepted safety reason. The 40-unit boundary still produces blocked with the same telemetry and rejection reason. The output matches the baseline. What changed is not behavior, but the construction boundary. One Rover protocol factory now supplies the entire product set. Hold both lines long enough to compare them, then return to the design rule. This version is not automatically better. If the application will always use one Rover protocol, the direct constructor is easier to read and has fewer types. Abstract factory earns its place when complete families vary and incompatible combinations are a real risk. It is especially strong when adding a new family means implementing the existing product contracts and one concrete factory. The weak side appears when we add a new product role. If every protocol also needs a diagnostics formatter, the abstract factory in every concrete factory must change. Direct injection also remains better when callers intentionally mix products or replace them independently. The decision rule is simple: protect a stable set whose members must vary together. Do not wrap unrelated objects in a factory merely because they are created near each other. We began with 4 direct choices that produced correct Rover behavior. The problem was not the output. It was that every caller had to preserve a relationship between the family name, command encoder, telemetry decoder, and safety policy. iMission Protocol Factory turned that relationship into a contract. Rover Protocol Factory became the concrete factory, and the 3 Rover classes remained concrete products behind their existing interfaces. Mission Session now receives one family boundary and keeps the same workflow. Part 2 will test the reason for this structure. We will add a complete orbiter family, choose the protocol at runtime, and leave Mission Session unchanged. That extension will show whether the compatibility rule truly belongs where we placed it.